Okay, so this is chapter 8, one of my favorite sections, 8A. We're going to be talking about linear versus exponential growth. So the first problem says basically you've got this straight town, and straight town has a population of 10,000 people in it. And it's going to grow at a constant rate of 500 people per year. So we've got this town, they're going to grow at 500 people per year. They started out at 10,000 people. Okay, but the next year they added on 500 people. So now they're at after year one, they're at 10,500. Then they've added on another 500 people. So 10,500 plus 500 would be 11,000. Added on another 500, which is going to be 11,500. And then by year 4, they've added on another 500 people, which is going to be 12,000 people. So when we come down here and look at the graph for Straight Town, what we're going to see is a pattern that is basically a straight line. Because when something is linear, it makes a straight line. So I'm looking at this blue graph. And the reason that it's going to make a straight line is because it had a starting point at 10,000, and then the first year we're adding 500, then we're adding 500 again, adding 500 again, and so it kind of just is even all the way out. So now Power Town is a completely different story. So they're still starting out a population of 10,000, okay, but in Power Town, their growth rate is at a constant rate of 5% per year. So we're talking about 5%. We know if we write that as a decimal, that's 0.05. So to get the next year, we're going to have to multiply by 1 to get back the 10,000 that we already had. But then we're going to have to multiply by 0.05 to get the extra 5% that we had. So if we take 10,000 and we multiply that by 1.05, again, the 1 is to get back what we already had, and the 0.05 is to get our extra 5%. Well, we're at 10,500, right, which is the exact same thing that happened over here. And if you look down here at your graph at year 1, they're still kind of close together here. Okay, but what happens when we do this again to get the next year? We multiply by 1.05 again. So that gives us 11,025. Still not that much more than year 2 here, just 25 difference. We're going to multiply again to get the next one. So I'm getting 11,576.25. Now we can't have 0.25 of a person, so we would drop that off. But I'm going to leave it just for multiplication's sake. Multiply by 1.05 again, and we've got 12,155.0625. Again, we can't have a decimal part of a person. But we're starting to really separate, okay? To get this, we added 500 to get to the next step every time. So that's the major difference here with exponential growth. When we have linear, when something is linear, we're going to add to get to the next step. When something is exponential, we're going to multiply to get to the next step. And if you compare these two graphs, you can see that if it's linear, Straight Town makes a straight line. If it's exponential, it kind of starts off growing slow, but then the more time goes by, it increases rapidly. Okay, so that by year 42, there would be a drastic difference between the two towns' populations. So again, linear, you're going to add to get to the next step. You're adding on, which is also multiplying. Okay, so if you wanted to talk about how this 500 happened in year 4, it would happen 4 times, but we're adding on to get to the next step. On this one, we're multiplying by the same factor every single time to get to the next step. So This one is definitely, this column is definitely linear. Go back up here. So this is our linear example, and this is our exponential example. Okay, so when we come down here, it says linear growth occurs when a quantity grows by the same absolute amount in each unit of time. Linear decay means a quantity decreases by the same absolute amount in each time. Exponential growth occurs when a quantity grows by the same relative amount, that is, by the same percentage, that's important. Remember on that problem, we had a 5% growth, and exponential K means the quantity decreases by the same relative percentage each time. So are these things linear or exponential? So when you're going through these examples, you want to kind of be able to recognize, okay, am I talking about something linear or am I talking about something that's going to grow exponential? Okay, so that first example says the number of students at Wilson High School has increased by 50 in each of the last 4 years. If the student population was 750 4 years ago, what is today? What is it today? So the first thing I notice is I don't see a percentage. We're not multiplying by a percentage. And we're just adding on 50 people every year. So this would be an example of something that is linear. If we wanted to figure out the answer to the problem, it says that the number of students at Wilson High School was increased by 50. That's going to be important in the last 4 years. This is important, by 50 in each of the past 4 years. If the student population was 750 4 years ago, so this would be our starting point, what we had to begin with. What is it today? Well, we've got 2 ways of thinking about it. Since we started out at 750 and 4 years have gone by, we could add 50 4 times. And this is what I was saying, that's the same thing as saying 750 plus 4 times 50 because it happened 4 times. And both of those would give us the same answer, which would be 950. So they have a population of 950, just 2 different ways to work the same problem. But this is linear because we're adding on the same amount every time period. The price of milk has been rising 3% per year. Because it's a percent, there's the number 1 clue. And they're wanting us, sorry, let me back up. They're wanting us to say whether it's growth or decay. This got bigger, the student population got bigger, so we're talking about growth. Okay. The price of milk has been rising 3% per year. So we know that we're having something that is getting, that is increasing, and it's increasing by 1%. So it's going to be exponential. And because it's increasing, it's going to be exponential growth. Okay. If the price of a gallon of milk was $4 a year ago, what is it expected to be now? So only 1 year has gone by. This would be our starting point. Okay, so all we would need to do is say 4 times, and I'm going to multiply by 1 to get back, I know it's going to be at least $4. So you multiply by the 1 to get back the $4 that you started with. And since only 1 year has gone by, it would be 0.03, and we would only have to do it 1 time because only 1 year has gone by. So the price now would be 4 times 1.03, which is going to be $4.12. Okay, and that's definitely exponential growth. Tax law allows you to depreciate. So depreciate means that something is decreasing, going down in value of your equipment by $200 per year. Okay, this is not a percentage, so this is probably not exponential. If you purchased the equipment 3 years ago for $1,000, what is its depreciated value today? So this is not a percentage. We're not multiplying to get to the next step. This is linear, and it is decay because we're losing value. We started at $1,000, but 3 years have gone by, and for each year, I'm losing $200. My equipment is depreciating by $200. Another way to write this problem would be 1,000 minus 3 times 200. Those would both get you the same thing. And the reason that I'm writing that in a different way is because if this happened over 20 years or something like that, we wouldn't want to have to write minus 200, minus 200, minus 200 20 times. That would be ridiculous. So we're down to $600. I mean, sorry, $400. And both of these would give us the same answer if we calculated them. So linear decay. The memory capacity of a state-of-the-art computer storage devices is doubling. Okay, so we are doubling something. We're not adding to get to the next step. We're multiplying by 2 to get to the next step every 2 years. This is happening every 2 years. It's going to double. So if a company's top-of-the-line drive holds 16 terabytes today, this is the starting point, what we have to begin with. What will it hold in 6 years? Well, we're multiplying to get to the next step, so that's going to be exponential. And it's growing, so we've got exponential growth. Okay, so we're starting at 16 terabytes. Now, it says how much will it hold in 6 years? Now, what you need to keep in mind is that this doubling happens every 2 years. So in 6 years, this is really 3 time periods that have gone by because 2 goes into 6 3 times. So one way we could write the problem is, since it's doubling, we're multiplying by 2, and we're going to do that 3 times. Okay, that will get us the answer. Or we could say 16 times 2 raised to the 3rd power, because we've got 3 time periods going by that's going to get us that answer. So 16 times 2 times 2 times 2 is going to end up being 128 terabytes. Okay, the price of high definition TV sets, the price of high definition TV sets has been falling by about 25% a year. So we've got our percentage, so that automatically means exponential for us. And it's something is going down, so that's not going to be exponential growth, that's going to be exponential decay because the price of TVs are falling. So we're talking about exponential decay. If the price is $1,000 today, well, that's your starting point. That's your starting point. What can you expect it to be in 2 years? Okay, so there's a couple of ways to do this problem. We could start out with a 1,000. I like to tell my students in decay, multiply by, you want to multiply by what you keep. Okay, here's what I mean by that. If it's falling, if the price is falling by 25%, okay, then we're losing 25%. But we are keeping the remainder. So if we're losing 25%, we would be keeping 75% because these two numbers would need to add up to 100. So 1,000, you want to multiply by what you're keeping. And since this is happening in 2 years, we would want to multiply by it twice. Another way to write that would be 1,000 times 0.75 raised to the 2nd power. Both of those would get you the exact same answer. Okay. Which is $562.50. Now the book teaches you a little bit different way and it has an extra step. I just think that this is easier, but it doesn't matter which way you work the problem, as long as you're working it in a way that's getting you the correct answer, and you're, I guess, mathematically correct in the way you're working it. So if you want to take that extra step, it's perfectly fine. So we've got a parable here. It says from hero to headless in 64 easy steps. It says legend has it that when chess was invented in ancient times, a king was so enchanted that he said to the inventor, "Name your reward." So, if you please, king, put 1 grain of rice on the first square of my chessboard, said the inventor, then place 2 grains on the second square, 4 grains on the third square, 8 grains on the fourth square, and so on. So what's happening? We're doubling. So he went from 2 grains on the second square, the third square had 8, so we were multiplying by 2. 8 times 2 would give us 16 on the fourth square. So the king gladly agreed, thinking the man was a fool for asking for a few grains of rice when he could have had gold or jewels. But let's see how it adds up for the 64 squares on a chessboard. So on the grain on the first square, this would be 2 to the 0 power. And anything raised to the 0 power we know is 1, because we're basically starting out with 1 grain of sand, and we're not raising it, we're not doubling it yet because we're still on the first square. Just be 1. And the formulas for the total grains of sand would be 2 to the first power minus 1. So on our second square, we're going to have 2 grains of sand, which would be 2 to the first. So now we have the 1 that we had before plus the 2, so we're up to 3. And to get that, we would do 2 squared minus 1. Okay. On the third day, we have 4 grains of sand, which is 2 squared. Our total grains of sand would be the 3 that we had here, plus the 4 that we have now, which is 7. And to get the total here, we would do 2 to the third minus 1, which you can see a pattern here. This is 2 to the first minus 1, 2 to the second minus 1, 2 to the third minus 1. So this should be 2 to the fourth minus 1, right? When you double 4, you get 8, which is 2 to the third. We take our 7 and add it to our 8 that we have now. That's going to be 15. And 2 to the fourth minus 1 is equal to 15. This would be 2 to the fifth minus 1, right? So on the fifth day, we have 16 grains of sand, which is 2 to the fourth. So we want to take for our total, we got 15 plus our 16 that we have now, which is 31. Okay, and if this pattern kept repeating for 64 days, well, we need a way to cheat here. So we know that, so I'm looking at 5 here, and I'm noticing that this is a 5. So this would be 2 to the 64th minus 1. We would be able to come up with that. It's going to be a really big number. And when we go here, look, this is 2 to the 4th, which is 1 less than this. So this would be 2 to the 63rd. We should be able to come up with that. Okay, I'm getting something huge that's too big to fit on my calculator. It's spitting it out in scientific notation. So approximately 9.22 times 10 to the 18th power would be the answer to this one. Okay, and so I'm going to skip this middle step because these two answers are the same. So if we do 2 to the 64th minus 1, this is going to be, I'm just rounding to 2 decimals. It's going to be approximately 1.84 times 10 to the 19th power. I used to tell my students when I taught high school to do this right around this time of the year because there are, right around Thanksgiving, we've still got several days till Christmas. We don't have 64, I think. But we have close to that. And I would tell them, don't do it with rice, though. Do it with pennies. Tell your parents that all you want for Christmas is 1 penny today, then double it and get 2 pennies tomorrow. The next day, get 4 pennies. So the same problem, but using pennies. And some of the parents actually fell for it because, look, if you do this for 64 days and we pretend this is pennies and not rice, this is the total. This is our grand total, 1.84 times 10 to the 19th power. Well, if we change that to regular notation, we know that we're moving our decimal 19 times. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. All of these are zeros now because we have to put them to hold the place value. Okay. So if we go back and add our commas, we can see that this number is huge. Now, one thing we do know is this is pennies. So in order to get it in dollars, we would need to divide by 2, which would take off 2 of these zeros. Now to get it rice, we would leave the 2 zeros on. This is how much rice we have. But if we were talking about pennies, we would divide by 2. We would take off 2 of those zeros. So we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 zeros. Okay, and if we put our decimal, okay, I know that this would be the 100,000s right in here, right? This would be, if we had a 1 here, this would be a 1 million. So this is 1 billion. So this is 1 trillion. So the next one, the next number, I don't even know if I know the name of that, but this is a huge amount of money. If your parents gave you a penny today, 2 pennies tomorrow, 4 pennies the next day for 64 days, and you got to add those on. That's an enormous amount of money. And several of my kids' parents fell for that around Thanksgiving to Christmas time. But okay, so the magic penny. One lucky day you meet a leprechaun who promises to give you fantastic wealth, but hands you a penny before disappearing. You head home and place the penny under your pillow. The next morning you find 2 pennies. The morning after that you find 4. Apparently the leprechaun gave you a magic penny. While you sleep, each penny turns into 2 magic pennies. So this problem is pretty similar to what we were just talking about. So we know that to write a penny, it would be 0.01. And we are doubling that penny. So the first day we would just end up with 1 penny, right? 1 cent. The second day it would be 0.01 times 2 to the first, which is going to be 0.02. The third day, now we're not, the difference in this problem and the problem before is we're not adding it on to the total that we had. We're just doubling every day. So in other words, we're not saying we get 2 pennies and then we're going to add that on to the next day. We're just doubling to get to the next number. So it's not going to be quite as big. 0.04, 0.01 times 2 to the third, 0.08. 0.01 times 2 to the fourth is going to be 16 cents, which this is not a lot right now. So for our formula to get any day, so T would represent any day, the day number, I guess. So 0.01 times 2 raised to the T power. So what would we have if we got to do this for 9 days? We would be 0.01 times 2 to the 9th. We would get a total for that. 30 days, 0.01 times 2 to the 30th power. 51 days would be 0.01 times 2 to the 51st power. Now the difference between this problem and the last problem is just simply that we're not adding on we're not getting to keep the pennies from the day before. So it's just doubling every time. So 0.01 times 2 to the 9th. Okay, that's going to give me $5.12. So not bad. By day 9, you're up to $5.12. By the 30th day, probably will like this number. We're up to okay, so $10 million. That's pretty big, huge number, right? So by the 51st day, 0.01 times 2 to the 51st power. The number is so big that it's giving me the number in scientific notation, so this is an approximation. But we would have to move our decimal 13 times, so 2, 5, that would move it twice. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We go back and add our apostrophes or our commas. That's this is a million, right? This place right here would be a million. So this is a billion, so approximately $22.5 trillion. So that's crazy amount of money after 51 days. And that's not adding on. So that number is a little bit smaller, like I said, than the other one. Okay. So this example, both of these examples are exponential growth because we are multiplying to get to the next step. Okay, we are doubling something. It's growing. It's getting bigger really, really, really fast. Okay, they're not linear. Linear would be just adding on something adding on the same thing to get to the next step. Okay. So the last parable that we're going to talk about today is this bacteria in a bottle. So it says, suppose you place a single bacterium in a bottle at 11 a.m. So it grows at 11:01. It divides into 2 bacteria. These 2 bacteria grow, and 11:02 you have 4 bacteria. At 11:03 you've got 8 bacteria, and so on and so forth. So what we have, right, is our starting point is that we have a single bacteria. So before any time has gone by, we have 1 bacteria. Then after 1 minute goes by, we have 2 bacteria, then we have 4, then we have 8 after another minute goes by. Now suppose the bacteria continue to double every minute and the bottle is full at 12. So 60 minutes has gone by from 11 to 12, the bottle is completely full. You may already realize that the number of bacteria at this point must be 2 to the 60th power because 60 minutes have gone by and you're doubling it every time. So that's where the 2 comes from. But the important fact is that we have a bacterial disaster on our hands because the bacteria have filled the bottle. The entire bacterial colony is doomed. So question number 1 says, the disaster occurred because the bottle was completely full at 12. When was the bottle halfway full? Well, because it took an hour to fill the bottle, many people guess that it was half full at 11:30. However, because the bacteria doubles in number every minute, they must also have doubled during the last minute, which means that the bottle went from being half full to full during the final minute. That is, the bottle was half full at 11:59. Okay, does that make sense? So if it is full at 12, then it doubles every minute. Then half of this at 11:59, it had to be halfway full. So for it to go from halfway to completely full, we would multiply by 2. So it had to be halfway full at 11:59. Question 2, imagine that you are a mathematically sophisticated bacterium, and at 11:56 you recognize the impending disaster. You immediately jump on your soapbox and warn that unless your fellow bacteria slow their growth dramatically, the end is just 4 minutes away. Will anyone believe you? So note that the question is not whether you are correct, because you are. The bottle will indeed be full in just 4 minutes. Rather, the question is whether others who have not done the calculations will believe you. As we've already seen, the bottle would be half full at 11:59. Continuing to work backward through the doublings each minute, we find that it would be a fourth full at 11:58. So basically we're saying at 12, we know that the bottle is full. So at 11:59, half of that, it would be half full. At 11:58, the bottle is going to be you would take a half of a half, and 1/2 times 1/2 is going to give you a fourth of the way full. Okay, if we move to 1157, it's going to be half of a fourth, which is just an eighth full. Okay, and so if we move all the way back to 1156, it would be 1/2 of 1/8, which is 1/16 of the way full. So when you look at that, that means that there's a lot of space left in this bottle. There's 15/16 space. So if it's 1/16 full, that means that 15 out of 16 is empty. So if the person is not familiar with this mathematics, if the bottle is 15/16 empty, I mean, that if we're talking about a bottle and we divided it into 16 parts, we're talking about like way down here is all that we would have filled up at 1156. Now they're probably not going to believe you if they don't understand this, how it's going to double. Okay, question 3. It's 11:59, and with the bottle half full, your fellow bacteria are finally taking your warning seriously. They quickly start a space program, sending little bacterial spaceships out into the lab in search of new bottles. Thankfully, they discover 3 more bottles, making a total of 4, including the one already occupied. Working quickly, they initiate a mass migration by packing bacteria onto spaceships and sending them into new bottles, just in time to avert the disaster. Given that they now have 4 bottles rather than just 1, how much time have they gained for their civilization? Well, because it took 1 hour, right? We know that it took 1 hour to fill 1 bottle. Got 1 hour, it's going to fill up 1 bottle. You might guess that it would take 4 hours to fill 4 bottles, but remember that bacterial population continues to double every minute. If there are enough bacteria to fill 1 bottle at 12, there will be enough to fill 2 bottles at 12:01, right? So at 12:01, there would be enough to fill 2 bottles. Well, what's going to happen at 12:02? We're going to have enough to fill 4 bottles, right? Because it's going to double every time. So the discovery of 3 new bottles gives the bacteria only 2 additional minutes. That's how fast, when you're talking about exponential growth, it grows really fast. It starts out slow, but once it starts taking off, it gets big really, really fast. So question 4, suppose the bacteria continue their space program, constantly looking for more bottles. Is there any hope that further discoveries will allow the colony to continue its exponential growth? So let's do some calculations. After n minutes, the bacterial population is 2n. So our formula, after n minutes, we know that we would have 2 to the nth power of bacteria. So for example, right, 2 to the 0, after no minutes have gone by, we had 1 bacteria to start out with, and that was what we had at 11 o'clock. Okay, 2 to the first power, well, that gave us 2 bacteria, and that is at 11:01. 2 to the second power will give us 4 bacteria, and that is at 11:02, and so on. So there are 2 to the 60th bacteria when the first bottle fills 2 to the 60th, which is going to be a really huge number, at 12 o'clock. And we would have at 2 to the 62, that would be whenever we have, that's 12:02. That is going to be 4 bottles filled up, which we already kind of talked about that. Suppose that somehow the bacteria managed to keep doubling every minute until 1 o'clock. By that time, the number of bacteria, so at 1 o'clock, we would have 120, because 2 hours have gone by, we would have 2 to the 120th amount of bacteria, which is going to be probably too big to fit on the calculator. Now we must figure out how much space they would require for this population. The smallest bacteria measure approximately 10 to the negative 7. So this is just something that we know. So we know that we have this 10 to the negative 7th micrometer meters, which is also 0.1 micrometer. This is going to be the size of one bacteria. Okay, if we assume that the bacteria are roughly cube-shaped, which we don't know, but the volume of a single bacterium, so we know if we want to cube something, it would be 10 to the negative 7 to the third power, which is 10 to the negative 21 meters cubed. That's how much space it would take up. Therefore, the colony of, so if we have 2 to the 120th bacteria in 2 hours times the space that they take up, which is 10 to the negative 21 meters cubed, that's going to be approximately 1.3 times 10 to the 15th meters cubed. With this volume, the bacteria would cover the entire surface of the earth in a layer more than 2 meters deep. So this would cover the entire surface of the earth in 2 hours. And it would be 2 meters deep. Okay. In fact, if the Dudleys continued for just 5.5 hours, the volume of bacteria would exceed the volume of the entire universe. So this question right here that says, well, how many bottles would the bacteria fill at the end of the second hour? Well, for this calculation, we start with the fact that the bacteria have filled 1 bottle at the end of the first hour. As we continue to double, it's going to fill 4 bottles at 12:02, and so on and so forth. So the number of bottles filled at 2 to the m, where m is the number of minutes that have passed since 12 o'clock, there must be 60 minutes in the second hour. The number of bottles at the end of the second hour is 2 to the 60th. So we know that after 2 to the 60th, it filled up 1 bottle. We know that. Okay, and I'm answering this question. I'm kind of carrying it over, sorry. That is 1.15 times 10 to the 18th if we do that calculation. At the end of the second hour, the bacteria would fill up approximately 10 to the 8, this number right here, bottles. Okay, because for the first hour, 2 to the 60th, it fills up 1 bottle. But then after that, every minute, we've got another 60 minutes that are going to go by, which equals this. For every one of those minutes, it's doubling. And so that's how many more bottles it would fill up. So to finish this real quick, after the second hour, the bacteria would fill approximately 10 to the 18th bottles. Using the rule for working with powers of 10, we can write 10 to the 18th as 10 to the 6th times 10 to the 12th, and recognize that 10 to the 6th is 1 million, 10 to the 12th is 1 trillion, so 10 to the 18th is about 1,000,000 trillion, which is the correct answer for this assignment. So this would be the number of additional bottles. So that is the end of Chapter 8, Section A. And we've talked about exponential growth versus linear growth. Exponential, you're going to multiply to get to your next step. Linear, you're going to add on to get to your next step. That's the key to that. We'll also go over the support in the next class.